Hey there, so this video we're going to be doing a crypto challenge from the Cyber Apocalypse CTF 2022. We're going to be going over how the columns have turned, which here is the info if you want it. The cliffs for this challenge is that there's a flaw in the pseudo-random number generator and the same value is always returned for the next number. And since we're given the last key, that means we have every single key and there's nothing in the encryption process that isn't reversible. So we just reverse the encryption and we're able to decrypt all the messages. So we're given the source code. Let's go ahead and take a look at it. So we'll see basically what's happening is they're generating a random 16-byte seed, running that, creating the random number generator from that seed. And then we see they're taking messages in the super secret messages, which is just some file they're reading the lines from. And then what they're doing is they're getting the next number from the random number generator, converting it to a string, and that's the key. And then that message and the key is what's inputted into this encryption function. And then the output of that, the ciphertext, is then concatenated into that file that we have right here. And then we just get these this messages here was generated for us. But basically what it's telling us is they figured out they found the last key. So our goal is going to be to try to figure out how to decrypt this messages given that we have the last key. So if we look, at this encryption function, what we see is the key is fed into this other derived key function, which does some stuff. Spoiler alert, like we don't actually care what this does. So I never actually bothered to figure out what it does, so I can't really explain that. And then we get the width, however long the key is we're going to carve up the plaintext into blocks of that size. Then we're going to transpose those blocks. Then what we're doing is we are kind of mixing up those blocks. So like the derived key is going to be an array. And so in that array, the index of this value is the block it's going to grab. It's going to reverse that block. So it's going to create an array. Basically, it's going to create an array, a list of rearranged blocks that have all been reversed, and then it's going to flatten it. And that is what the ciphertext is. So if we look at this, there's actually nothing in here that isn't reversible. Like we're just flattening something. We can unflatten things. We are just mixing things up and reversing them. Well, we can unreverse something and then we can rearrange what it was. The reverse of a transpose is just another transpose, and then so we carved it up. We can uncarve it. We can just put it back together. So really, if we know the key, we know, and we have the ciphertext. If we had the key that built that ciphertext, we can decrypt it because we can just write a function to reverse that. So kind of the challenge then is going to be to look at this pseudo-random number generator and figure out, knowing the last key, if there's a way to find out what the previous keys are. So looking at it, when this class is initialized, there is some constant p. This is just some number. This is the hexadecimal representation of it. Now I'm curious, it doesn't really matter, but it is. There you go. That's the number. So glad I know. They're setting A and P to be equal to each other, and then B is just some random 16-byte integer. And then when it's initialized, this Rn is whatever the seed was, which the first time through was this, just another random 16-byte integer. And the way they're getting the next number is it is going to be equal to A times Rn plus B modulo P, and that's what they're returning. So if you're not familiar with modular arithmetic, not really going to explain it because there's just way better resources. But basically, what kind of one of the easiest ways it gets explained is like the modulo is basically just divide whatever this number is by p, and the remainder is what Rn is going to be. And that's kind of really all you need to know in order to solve this. Because let's take a closer look at what's going on here. So we know A and P are equal to each other. So let's just go ahead and make it a little easier for us to understand. So we're multiplying some number by P, we're adding it to it, and some other number to it, and we're dividing by P. So see, like, what would happen if we had, say, like 17 times some number plus some other number, doesn't matter, 53, and we're going to divide that. We're going to do that modulo. Actually, I should do it. Let's do 11. Modulo 17. Well, if you think about it, 17, so we have some multiple of 17, and we're adding 11 to it, and we're dividing it by 17. Well, when we divide by 17, we're basically, all the multiples of 17 are going away, so we're just going to be left with 11, right? 11 more than some multiple of 17 divided by 17 is just going to be 11. Well, that's the exact same thing that's going on here, right? We have some multiple of P plus some number B divided by P. Well, what that means is when we divide it by P, we're just going to have B left over. Like if we look back at this equation, right? If you divide both sides by 17, well, the way modular, that wouldn't work if you do it that way, but the way modular arithmetic works, right? This is going to be 0, and you're just left with 11. That might have made it more confusing, but so that's what we're doing here. So basically, every single time through, we're going to get what B is. B is always going to be the next number, and B is just some random 16-byte integer when it was initialized. Well, we know what B is then because we have this key here, this final key. And since we've said every single time it's always going to be B, it's always going to be B, we know what B was when it was initialized. And so we know there, right, because we have one, we've got all of them now. So essentially, we know what the key is now, so we can write the reverse of this function, which is why I said we don't really care what this is, because what we could do is, let's just do, and then, oh, where's our key? Here we go. And it was a string. So what is derived key of key? So this, right, since key is always the same every single time, derived key is always going to be that same array. So we don't even care about what that does. We just make it do it because we're always putting the same thing in, so we're always going to get the same thing out. That's how functions work. Well, I guess it could be randomizing something in there. So that would be, I guess, good to have checked, but I didn't do that, so whatever. And then actually that would make it reversible. Anyway, whatever. And then width is, what is the length of our key? 15. So we know, again, this doesn't really matter, right? I'm just doing it to make it kind of easier to read for us. So we know when the blocks were encrypted, these were always carved up into 15. And it looks like these are, how long are these? 105, so that would be 7 7 blocks of 15. So when we so this is an array of 7 rows, each 15 long. Then when they transposed it, it became 15 rows, 7 long, and then that's why the width here. So width is always 15. So it's basically, that's what it's using to rearrange everything and reversing it. So kind of rambling, but basically let's just go ahead and write our solution, because we have enough now to go ahead and do that. Let's see, how should we do this? We're gonna need to know these. These are our ciphertexts. Guess I should have done this before I made a video, so you didn't have to sit here and watch me do this. But it's kind of on you for not, well, maybe you're doing that and you're still like, ugh. But yeah, basically I was going to say, you should always watch videos at 2x speed, especially when it's people like me just kind of rambling on. Once you get used to it, it really is helpful. And then if you're doing that and then you take it off 2x, you'll be like amazed at how slow everyone sounds like they talk normally. So let's go ahead and steal a couple of these functions, right? We're gonna, the reverse of a transpose is a transpose, so we can just use this same array. And then I think we're gonna want to flatten too. So we'll just steal their flatten function. And then we'll write our own decrypt function. Now we know the derived key because it is always that. Oops. So let's go ahead and just, we're going to do the reverse of everything, and you do it in reverse order, right? So let's just go ahead and make a note so it's easy for us to understand. So we'll do the reverse of the twisted columnar encrypt. So the first thing they did this way is they flattened. So we want to unflatten. So let's call that blockify. We're going to make blocks. And then so you work from the bottom up, do everything backwards. So they reversed and mixed. We're going to reverse everything. And then we're going to put back in the order it was originally. The reverse of, where are we? The reverse of a transpose is a transpose. And then the reverse of blockifying we'll call flattening. And then we're done. So let's just go ahead and implement each of those. So like we want to unflatten, which means we want to create a block or blockify. So we'll say our CT blocks equals, we'll just kind of do the opposite of what they did. So we know we went from 7 rows of 15 here to down here we had 15 rows of 7. So we want to do 7, I plus 7, I range 0, length of the ciphertext 7 at a time, right? And then we want to reverse everything. So we just do it the same way they did. For CT and CT. I guess we could have just combined these two, right? Whatever. And then we're going to put it back in the order they were in. So we'll say, I think of how I want to do this. Let's just do blah equals 0. This is kind of sloppy, but I didn't really plan this out very well. And then we are going to get, just like they did, we'll do the derived key. Index I plus 1 equals CT blocks I. And then we're going to transpose that. So plain text equals transpose of our blah. And then we're going to flatten. So PT equals flatten PT. And then we'll return PT. Then, so we want to do that. We want to do that for each of the ciphertext in the ciphertext. So we can just say for ciphertext in ciphertexts, plain text equals, I spelled decrypt wrong, but whatever. And then let's just print it out. So this is reverse of that function. Let's see how many stupid typos I made, and if it works. Oh, so it did work first time through. And this is kind of like really annoying and hard to read. And if I remember right, where was the key? It was right here. So this is actually kind of confusing for me when I did it, because I was like, well, does it carry on? Is it supposed to be? But basically you just, I would input it and show you, but I've already gotten the flag. But basically you just take that, and then it was stick that in there. So the LCG is vulnerable. We need to change it. So there you go. That's how that challenge went. So if you have any questions, I did a terrible job explaining something, feel free to leave a comment. Let me know. I'll happily try and go over something better. If you watch this video, I hope you got something out of it. If you're still listening, I appreciate it, and I hope I was able to help. And yeah, I hope you had a lot of fun in the CTF. And yeah, that's it.